Now we'll discuss adiabatic process in detail. As we already briefed about it, that in this process, no heat exchange takes place between system and surrounding. Or we can state simply here dq is equal to 0. No heat is either supplied or rejected by the system. So we can state from first law of thermodynamics, which gives dq is equals to du plus dw. So here the term of dq is 0. So we can always write dw is equals to minus du, which signifies a very important situation where we can say if work is done by the gas, it is doing work by its own internal energy, so internal energy will decrease. So we can state here for work done by gas, internal energy of gas decreases. And for work done on gas, if external mechanical work is done on gas, that means dW is negative, so obviously du will become positive. So this amount of work will increase internal energy. So we can write internal energy of gas increases. So we can state if work done by gas means gas is expanding. On expansion of gas, its internal energy decreases, that means temperature will decrease. So we can say always, you just keep this note in your mind because there's quite a useful relation in day-to-day life as well as in various applications. Always in adiabatic expansion, where in expansion work is done by the gas, in adiabatic expansion temperature of gas decreases, or we can say the gas cools down on expanding. And in adiabatic compression, temperature of gas increases. There are many various applications which gives us an idea about adiabatic expansion and adiabatic compression. We'll discuss in coming sections. As we have studied that in an adiabatic process, net heat exchange between system and surrounding is 0. So always remember that all quick or sudden processes in nature are always taken as adiabatic processes, because all sudden or quick processes, the time involved is very small and the flow of heat is a gradual or a slow phenomena. So in a sudden or quick process, a phenomena which is executed in a very short span of time, if time is not sufficient, no heat flow takes place. So even if the process is carried out in a thermally conducting environment, the process can be taken as an adiabatic process, because no heat exchange will take place due to less duration of time. So always remember, all sudden or quick processes in nature are considered to be adiabatic. Now we can analyze the various thermodynamic parameters in an adiabatic process. So we can write for adiabatic processes, if we talk about heat supply, we can directly write in case of calculation of heat supplied as dq is 0. That means in any part of process no heat is being supplied, we can write the total heat is always 0. If we talk about change in internal energy, so again we can write change in internal energy remains constant for any two states of a gas, no matter whichever path is being followed. So delta U can always be written as NCV T2 minus T1, or if we write CV in terms of R, it can be written as NR by gamma minus 1 T2 minus T1. It remains same. If we calculate the work done by gas, we have studied that gas does work in adiabatic process by variation in internal energy, as no external heat is being provided, so it is always minus delta U. So this can be written as NR by gamma minus 1 T1 minus T2. Mathematically, this nRT1 and nRT2 can be written as P1 V1 minus P2 V2 by gamma minus 1. So these are the relations we use as thermodynamic parameters for an adiabatic process. Now, if we analyze the ID curve for an adiabatic process, then we must be aware about that to plot an ID curve we need a process equation. So we can directly write for plotting ID we need P equals to F of V relation. Without this relation we cannot plot the curve because the curve is plotted between pressure and volume axis. Unlike to the case of isochoric, isobaric and isothermal processes where P equals to F of V relation was defined under the process only, here we cannot directly get the process equation, we need to derive it. So first thing we must know how to derive process equation. For a thermodynamic process, if it is not directly given, so if we talk about derivation, we can say for all thermodynamic processes, always keep the statement in mind. For all thermodynamic processes, the process equation P equals to F of V can be obtained by combining two differential equations. These are first equation is differential form of first law of thermodynamics, which is written as dq is equals to du plus dw, and the second is differential form of gas law, ideal gas law, which is written as pdv plus vdp is equals to nrdt. This we already studied in previous articles of the same topic. Now combining these two equations we can easily get it. Let's analyze. Here we can write, say if there is equation 1 and there is equation 2. So from 1 we can write and this dq is 0. So here du is minus dw. So we can write du as nr by gamma minus 1 dt, which is equals to minus pdv. You can see I have substituted du as n cv dt and this is equals to minus of dw, which is minus pdv. Now we can easily substitute the value of nr dt from this relation. This gamma minus 1 can be taken on other side of equality. So this will become pdv plus vdp is equals to negative of gamma minus 1 pdv. Let's continue it on another sheet. If we further simplify the expression, we are going to get pdv plus vdp is equal to minus gamma pdv plus pdv. Here this pdv gets cancelled out and we can rearrange the variables. This will give us dp by p is equals to minus gamma dv by v. If we integrate the two expressions indefinitely, this will give us ln of p is equals to minus gamma ln of v plus a constant of integration. So on taking this term on left hand side and gamma on the power of this argument, this will give us ln p plus ln of v2 power gamma as a constant, and here we can write as ln of pv2 power gamma as a constant. Obviously in this situation we can write pv2 power gamma as a constant. So this is the relation which we can state as the process equation of pressure and volume. So in this situation, if we wish to plot the indicator diagram, that can be very easily plotted as here we can write P is equals to some constant by V2 power gamma, or P is inversely proportional to V2 power gamma. Here we can state as always gamma is more than 1, the graph will be plotted with a slope slightly higher than the isothermal curve, which depends on gamma. If we plot it between pressure and volume, the graph will look like this shape. If in a state 1, the volume and pressure are V1, P1, and in a state 2, volume and pressure are V2, P2, the graph can be plotted like this, which is the inverse proportionality curve with the V2 power gamma. We can analyze the curve with its relative position with respect to isothermal curve. We will discuss in detail. First, let's analyze in detail about the process equation for the adiabatic process in different forms, as this process is mainly used to relate the thermodynamic coordinates in different states of a gas. As we already discussed, that process equation for an adiabatic process can be written as PV2 power gamma as a constant. And this equation we can use to relate pressure and volume for two different states of a gas. So we can write for two states of a gas under adiabatic process, we can write P1 V1 to power gamma is equals to P2 V2 to power gamma. This is the relation we use for relating thermodynamic coordinates, pressure and volume for two states of a gas which is undergoing adiabatic process. Now we can also relate temperature and volume, as P can be written as nRT by V by gas law multiplied by V2 power gamma is constant. So here nR is again a constant, so this can be written as T V2 power gamma minus 1 as a constant. So using this again we can relate temperature and volume as T1 V1 gamma minus 1 is equals to T2 V2 to power gamma minus 1. This also we can use as an equation to relate temperature and volume. Now from this first relation we can also substitute V as nRT by P. From here we can write P multiplied by nRT by V to power gamma is a constant. Here we have substituted V as nRT by P. So in this situation, nR is again a constant, so this can be written as T gamma P1 minus gamma is a constant. So using this we can relate temperature and pressure as T1 P1 with power of T as gamma, power of P as 1 minus gamma is equals to T2 P2 with power as gamma and 1 minus gamma. This is the relation we can use to relate temperature and pressure. Similarly, as we have drawn the curve between pressure volume, we can draw the curve between temperature volume and temperature pressure also. These three are quite useful relations we are going to use in various kind of numerical applications.